Welcome to the course Introduction to Mobile Robotics. Now we are seeing the Module 4. We'll go to the next important topic that is related to mobile robotics. In real world robotics, no sensor is perfect. Every sensor has strength, but it also has weakness. For example, wheel encoders are simple and reliable for measuring motion, but over time they accumulate error due to wheel slip. An IMU gives fast orientation updates, but small biases in acceleration or gyro measurements grow into large drift errors. Cameras depend heavily on lighting conditions, and LiDAR may struggle with reflective or transparent surfaces. If we depend only on one sensor, the robot's understanding of its position will gradually degrade. This directly affects navigation, obstacle avoidance, and decision making. Sensor fusion addresses this issue. Instead of trusting a single sensor, we combine multiple sensor measurements. By doing so, the robot reduces uncertainty and improves reliability. In simple terms, sensor fusion allows the robot to make smarter decisions by cross-checking information from different sources. Concept of sensor fusion. The key idea behind sensor fusion is complementarity. Different sensors observe different aspects of motion and environment. Some sensors provide accurate short-term measurements but drift over time. Others provide global reference information but at lower frequency or higher noise. When we combine them mathematically, the strength of one sensor compensates for the weakness of another. For example, odometry gives smooth motion updates but drifts slowly. A camera or LiDAR can detect landmarks and correct that drift. When these are fused, the robot maintains both smooth tracking and long-term accuracy. So fusion is not just mixing data, it is intelligently combining information to produce a better estimate than any single sensor could provide. Now we'll see a simple example connecting the odometry and IMU. Suppose a robot has wheel encoders and an IMU. The encoders estimate displacement by measuring wheel rotations. However, if the floor is slippery, the wheels may rotate without actual movement. This introduces error. On the other hand, the IMU measures angular velocity and acceleration, but integrating acceleration twice to obtain position introduces significant drift. Now imagine combining both. The encoders provide reliable short-term translation updates. The IMU provides fast orientation updates. By fusing them, even using a single weighted average, we can improve heading accuracy and reduce drift. This example shows the essence of fusion. Two imperfect sensors, when combined, produces a more accurate estimate. Earlier, when we discussed localization, we assumed that motion updates were exact. We treated the robot's position as a precise value. But in reality, every measurement has noise. Wheel slip vibration sensor bias all introduce uncertainty. So instead of saying the robot is exactly at this position, we say the robot is likely to be somewhere within this region. This introduces the idea of probability distributions. Rather than a single point estimate, we represent the robot's pose as a distribution that reflects uncertainty. This shift from deterministic estimation to probabilistic estimation is fundamental in modern robotics. It allows us to handle noise in a mathematically consistent way. In probabilistic localization, we introduce the concept of belief. Belief represents the probability that the robot is at different possible states. During prediction, the robot uses its motion, model, and control input to estimate where it might move next. Because motion is uncertain, this step increases uncertainty, the distribution spreads. During correction, sensor measurements are used to adjust the belief. If a measurement matches a predicted state, the state becomes more predictable. This reduces uncertainty. This recursive process follows Bayesian reasoning, combining prior knowledge with new evidence. The Bayesian filter provides the mathematical structure for this process. At every time step, two operations occur. First, the motion update. The robot predicts its new state based on control inputs. This spreads the probability distribution because motion is uncertain. Second, the measurement update. Sensor data is used to correct the prediction. The distribution becomes concentrated around state consistent with the measurement. This cycle continues repeatedly as a robot moves. Conceptually, the prediction increases uncertainty, correction reduces uncertainty. This framework forms the foundation of most modern localization algorithms. One of the simplest probabilistic method is histogram filter. Here we divide the environment into discrete cells. Each cell stores the probability that the robot is located there. When the robot moves, the probabilities shift according to the motion model. When a sensor measurement arrives, each cell's probability is adjusted depending on how well it matches the measurement. Although this method becomes computationally expensive for large maps, it is conceptually very clear. It helps students visualize how probability distributions evolve. It is an excellent starting point for understanding probability localization before moving to more advanced techniques. The Kalman filter is used when system dynamics are linear and noise follows a Gaussian distribution. Instead of storing the full probability distribution, it summarizes belief using just two parameters, mean and variance. The mean represents estimated state, the variance represents uncertainty. During prediction, the mean is updated and the variance increases. During correction, the estimate is adjusted based on measurement and the variance decreases. The Kalman filter provides optimal estimates under Gaussian assumptions. It is widely used in IMU GPS fusion and many engineering systems. For this course, focus on understanding idea rather than mathematical deviation. The particle filter is more flexible than the Kalman filter. Instead of representing belief using mean and variance, it uses many random samples called particles. Each particle represents a possible robot state. After motion, each particle moves according to the motion model. Then sensor measurements are used to assign weights to particles. Particles that better match the measurement receive higher weights. Through resampling, unlikely particles are discarded and likely ones are duplicated. This method works well for nonlinear systems and complex noise patterns, making it very suitable for real-world robotic applications. To conclude, sensor fusion and probabilistic localization are deeply connected. Sensor fusion provides multiple measurements from different sensors. Probabilistic localization provides the mathematical framework to combine those measurements while accounting for uncertainty. Together, they allow robots to operate reliably in uncertain environments. Without probabilistic methods, sensor fusion would be inconsistent. Without sensor fusion, probabilistic localization would lack sufficient information. These concepts form the foundation for the advanced topics such as SLAM and autonomous navigation.